Welcome to qnawire.
Here we will let capital omega be the angular velocity of the cab for the helicopter. And we will let the small omega be the angular velocity of the blades relative to the cab. So that's the angular velocity of the blades relative to the cab. And so the absolute angular velocity of the blades is capital omega plus little omega. And we'll come back to this later on. So the data that we are given is that initially the angular velocity of the blades relative to the cab is 180 revs per minute. 180 RPM converts to 6 pi radians per second. We know that 1 rev has 2 pi radians and 1 minute has 60 seconds. The second state has omega 2, the angular velocity of the blades relative to the cab changes to 240 revs per minute. And this calculates to 8 pi radians per second. So we have the small omega for each state. We're also given the moment of inertia for the cab, IC, is given to be 650, and that's in pound foot second squared. For the blades, the mass moment of inertia is equal to 4, and it's modeled as a thin rod, so that's 1/3 ml squared. And this is equal to 4 into 1/3 multiplied by its mass, which is its weight, 55 pounds, over 32.2, which is G, and L is 14, and that's squared. And so we get the mass moment of inertia for the blades in the same units as the cab is 446.38, and that's pound foot square seconds. So now we have the angular momentum of the cab and the angular momentum of the blades. So the first thing we're going to do is we'll assume that capital omega 1 is equal to 0. So the angular velocity of the cab in the first position is equal to 0. We're then going to look at the conservation of angular momentum. We're going to use the conservation of angular momentum about the shaft to set up an equation. And so the angular momentum in position 1 is due to the blades is the moment of inertia for the blades plus the absolute angular momentum of the blades, which is omega 1, small omega 1 plus capital omega 1, plus the angular momentum of the cab, which is IC, capital omega 1. And in the second position, the angular momentum due to the blades is IB into small omega 2 plus capital omega 2, where subscript 2 is for position 2 or state 2, plus mass moment of inertia for the cab times capital omega 2. And so if you rearrange this equation, we can make capital omega 2 the subject of the formula. And this is in essence what we wish to calculate for. So this is minus IB into small omega 2 minus small omega 1 over IC plus IB. Remember, we've assumed that capital omega 1 is 0. And these we have values for. We can actually substitute our values in here. So this is minus 446.38 for IB into 8 pi radians per second minus 6 pi radians per second, omega 2 minus omega 1 over IC plus IB is 446.38 actually, plus IB is 650, or IC 650, and hence we get omega 2. So this is the velocity of the cab, the angular velocity of the cab in state 2 to be minus 2.5581 radians per second. And this translates to, so capital omega 2 is equal to minus 24.4 RPM, or revs per minute.